Hi. In this video, we'll continue our analysis of a sum of n numbers. But what we look now is to see how the time is growing if we increase or decrease n. So how the execution time is uh, growing compared with the growing of the number of numbers that we add. So let's create a small uh, program that will create a table in order for us to do this analysis. And we'll save it in the class sum growth analysis. The test addition method will remain similar with the previous one, just that we have the name as a parameter, and also will provide the number of executions and the n, which is the last value that we add. Now the print will be modified because now what we want to do is to modify the last values that we add. This one will be modified. And to do that, we'll start from an initial value. We'll have an increment that at each row will increase this minimal value, and we'll grow until we reach a maximum value or go over it. So we'll go up to the maximum value. So also we'll have a constant number of execution for all these values. Now, sure, we start with a header showing what we want to obtain, and then we'll have a for that will go through all the values. We'll pick an n for all these values, so the number of numbers that we want to add, and we call the test addition to compute the time analysis for each trial. Now, each for each n, we'll use the same number of executions. After that, we print the results in the table. So we print the n and the mean that we obtain for our sample, minimal value, maximum value, and the confidence interval for our sample. Given this, we will have now the main method that will just will compute the sum of the first integers from 10 millions to 100 millions, going from 10 to 10 millions. And for each value starting with 10 million, we'll run our program 41 times. So in order to compute the mean time. So if we do that, let's see what we obtain. So this is a table, and it's the sum of the first n integers, and the sample size, as I said, it's 41. And now we run for various values, and we get these means. So this means all of them look fine. There is an anomaly here at 20 millions. It's very big. Probably something happened when I run. Some process in background started, or something happened with the computer. You will always have these kind of outliers when you run executions, because your computer is not a perfect machine. It's doing many things in the same time. So the experimental execution will always be different from any kind of theoretical execution. So this is a table, but before analyzing this table, let's look at the theory. Let's try to understand what will be the order of growth from a theoretical point of view. So if we look at the code that is tested, we start by declaring the result, a sum equals 0. From the point of view execution, this is constant, so will be considered as 1. Then we have a for, and the for is going from 1 to the last value added, which is, in our case, we also name this n, the number of numbers that we want to add. So I will go from 1 to this n and do something. So basically I have n times doing something. So the estimated order of growth will be n times the order of growth of the block, what I do in the block. And in the block, I do just a sum. I add I to my sum. So I add the current value to my sum. So this also will be a constant time. So again, the order of growth is 1. So basically what we obtain, let's say 1 plus n times 1, which is sure a linear order of growth that depends on n. So what we obtain based on the theoretical analysis is linear growth. Now let's do an experimental analysis and see what the experiments that we run is telling us. So we obtain this table, and let's plot, let's draw the value. So we'll put the x value as the n and the y value like the average mean time that we computed. And except the first value that it's very low, and when the values are low, they may have some more errors. And the second value, which seems like another type of kind of error, then we obtain a pretty linear description of all the values. If you look, it's like a line going through them. So if we ignore the first two values, and again, we ignore them. If you run again and represent graphically, you may get completely another graph and other outliers. So generally, if you see outliers like these first two values, we'll ignore them. But all the others form a very smooth line. Even the first value, it's almost on that line, but it's a little bit upper. So um, that's very important because this confirms our linear growth. As n is growing, the execution time is growing, and it's a linear growth relationship between the numbers that we add and the mean execution time.